All right, so we're starting into chapter 3, talking about exponential and logarithmic functions. That's what chapter 3 is all about. Today we'll talk about exponential functions and what they look like. So we've talked about trigonometric functions. That's what we did. We spent most of the first semester on. We just finished talking about polynomials and rational functions. Along with exponential functions, those are the three major types of functions that you're ever going to work with. And the exponential and logarithmic functions are very important. Exponential functions have a lot of applications. They model population growth. They model radioactive decay. One of the big places, one of the big examples that we'll use exponential functions for is for interest, compound interest. We'll calculate compound interest with exponential functions. So it's an important family of functions, and then along with the logarithmic functions, the logarithms are the inverse functions of exponential functions. So we'll have hit all of the major types of functions that you'll end up working with. So let's remember what an exponential function is. Need a calculator, Caitlin? So an exponential function is a function that looks like f of x equals a to the x. So our variable is our exponent. And a is greater than 0, and a does not equal 1. So if a equals 1, we just get a line. 1 to any power is still just 1. So we don't want a equal to 1. Some of the properties of exponential functions, important properties. The domain is all real numbers. So we can put any number in for x, and it doesn't give us a problem with an exponential function. The range equals all numbers greater than 0. And we can write that as 0, infinity. We could write this as minus infinity, infinity. For every exponential function, the y-intercept is the point 0, 1. When x equals 0, our exponential function equals 1. So every exponential function that looks like this always goes through the point 0, 1. It crosses the y-axis at 1. Y equals 0 is a horizontal asymptote. So every exponential in this form has y equals 0 as a horizontal asymptote. F is increasing. If a is greater than 1, and f is always decreasing if a is less than 1. So if a is a fraction, our exponential function is always decreasing. So this y-intercept, that's an important one to remember for exponential functions. And y equals 0 is a horizontal asymptote is another important one to remember. So let's look at how we graph a couple of these exponential functions, just to remember what they look like. Any questions before we go on? And again, these are all things that we've seen at one point or another in the past. And when we look at a graph, the graph will look familiar also. So I'm going to set up a grid page. All right, so we're going to graph f of x equals 2 to the x on this page. Let's draw our axes. There's my y-axis. There's my x-axis. And we know that all exponential functions go through the point 0, 1, so we have a point here. We know our graph is going to go through that point. And we'll just calculate some additional points. So let's calculate f of -2, so over here, equals 2 to the -2, which is the same as 1 over 2 squared, which is 1/4. So at -2, we have 1/4. We have a point here. At let's calculate f of -1 equals 2 to the -1, which is the same as 1 over 2. So at 1, we have 1/2. F of +1 is just 2 to the 1, which is just 2. So we're up here, 1, 2. And f of 2 is 2 squared, which just gives us 4. So 1, 2, 3, 4. So there's some points. We know that y equals 0 is an asymptote, so I can sketch my graph, just connect these smoothly like so. And my function looks like that. So that would be a graph of 2 to the x. And knowing that it goes through 0, 1 is helpful. Knowing that any exponential function goes through 0, 1 is going to be helpful when we're sketching a graph. And the reason that is any number a to the 0 equals 1 for any number. And we'll do a little practice with rules of exponents tomorrow, because we'll be using exponents a lot in this unit. Any questions on our graph? So this is what an exponential function with a number bigger than 1 as our base. This is what an exponential function is going to look like. Some variation of this. So let's look at another graph. Let's look at, we want to graph f of x equals 2 to the minus x. 2 to the minus x is the same as 1 over 2 to the x, and that's the same as 1/2 to the x power. All of these mean the same thing. So we're going to graph this function. We know since our base is between 0 and 1, we know that our graph is going to be decreasing everywhere, where our last graph was increasing everywhere. So let's draw our axes here. We have y and x. We know it's going to go through the point 0, 1, so it's going to go through this point, and we'll calculate some additional points. So let's calculate f of 2. F of 2 is 2 to the minus 2. I'm putting in 2 up here for x, equals 1 over 2 to the 2 equals 1/4. So f of 2 is 1/4. F of 1 is 2 to the minus 1, which is the same as 1/2. So there's my point at 1, 1/2. Let's calculate f of minus 1. So that's 2 to the minus 1, which is just 2 to the 1, which is just 2. And f of minus 2 is 2 to the minus 2, which is 2 squared, which is 4. So here is my point 2, 1, 2, 3, 4, up here. So now I connect these in a smooth curve. And my graph is going to look like this. So when I have a fraction as my base, or when I have a negative exponent, I have a function that's always decreasing. Y equals 0 is an asymptote. It never gets down to 0, and it takes on every value between 0 and infinity. It's going to always decrease and approach 0 as x gets very big. Is this ringing some bells from what you've done before with exponential functions? Yeah. All right, so exponential functions transform just like any other function. So I'm just going to talk really quickly about transformations. And by transformations, I just mean shifting. Exponential functions shift just like any other function. So if our parent function were 4 to the x, if 4 to the x plus 2 is going to shift 2 units left. Just like parabolas, just like when we did sine functions and cosine functions, when I add or subtract to my x variable, I'm going to shift left or right. So this is going to shift 2 units to the left. For x plus 2 minus 3 would be 2 left, down 3. If I did minus 4 to the x, it's going to reflect over the y-axis, and 4 to the minus x is going to reflect this should be reflect over the x-axis, and this one reflects over the y. And this is what we just saw when we graphed our 2 functions, 2 to the x and 2 to the minus x. If we go back and look, here's 2 to the minus x, and here's 2 to the x. they're reflected over the y-axis, reflections of each other over the y-axis. So they transform just like any other function. So I'm not going to spend a lot of time on that. You guys are good at transformations already. You understand how the transformations work. They work with exponential functions. They work the same way. Questions before we move on? Okay. One important concept with exponential functions is called the natural base. And the natural base is a very important number in mathematics called e. This number originally was discovered when people were calculating tables of compounded interest. And they said, what happens when we compound interest continually? And they came up with this number. Where it comes from is the expression, and I'm going to make a little table here. If we do 1 plus 1 over x to the x power, as x gets very big, this equals the number, our special number e. E is like pi. It's an irrational number. It's a non-repeating decimal. It goes on forever. And that's why you have to give it a special symbol. But it comes up in lots of different contexts. It comes up in science. It comes up in optics. It comes up in waves. It comes up in quantum mechanics. It comes up in so many different places that we give this number a special symbol. We call it.
Does it have like a value?
Yes, and we're going to talk about that in just a second. So let me make a quick table here where I calculated this out just to show how this works. And I'm going to do 1 plus 1 over x to the x. So if x equals 1, I'm just plugging in my x into this. If x equals 1, this expression turns out to be 2. If x equals 10, I did all the calculations for you. If x equals 10, we get 2.594. If x equals 100, I get 2.705. If x equals 1,000, we get 2.717. And if x equals 10,000, we get 2.7181. And if x equals 100,000, this expression comes out to be 2.7183. So e is approximately 2.718, but it's just like pi. The digits go on forever and they never repeat. So it's a number that has properties a lot like pi, and it comes from this expression, and we use this expression when we calculate compound interest, and we'll talk about that in just a second. But e is a very, very important number, and we're going to be using that as the base of our exponential functions in a lot of cases. So I just wanted to talk about it because we're going to use this as our base for a lot of things. So just keep this in the back of your head, that e comes from this expression as x gets very large. Originally, it was discovered when calculating interest, which we're going to start talking about here right now. So compound interest is one of the big formulas that we use exponential functions for, to calculate interest. So if we want to say, we say that a equals the amount of money that we have. And P is our principal. P is the amount that we invest, or the amount that we start with. And X is the interest rate. As a decimal. And N is the number of pay periods. So N would be like quarterly, daily, semi-annually, that kind of thing. So if N were quarterly, our number of pay periods per year would be 4. And I should say, for our interest rate, for what we're talking about today, we're talking about the annual interest rate. So the way we come up with this formula for compound interest is our first, we start off, we want to figure out how much we have. So our first amount is our principal. And we compound our interest, we earn interest on it one time. So we get our principal times our interest rate. So after one compounding, after we earn interest one time, this is how much we have. And I could factor out the P and write this as P times 1 plus X. Now when our interest is compounded on this amount, our second, when we calculate this again, we get P times 1 plus X, that's how much we have now, plus P times 1 plus X times X. I'm earning interest on this amount now. And now I'm going to factor out the P times 1 plus X. That's common to both terms. That's P times 1 plus X times 1 plus X. I'm just factoring out this factor of P times 1 plus X. And that is P times 1 plus X squared. If I do this again, now I'm going to earn interest on this amount. After I earn interest again, I get P times 1 plus X squared plus I'm earning interest on this amount now, P times 1 plus X squared times X. Yes?
Where is the X going to the end of this thing?
Of this one?
Yeah.
So after I earn my interest, I have this amount of money plus the amount of interest I earn on this amount of money.
Yeah.
So I have this amount, the amount of interest I earn on this amount of money is P times 1 plus X times my interest rate.
Right. So where is it going? Factor out the P times 1 plus X.
If I factor out the P, if I factor out a P times 1 plus X from this term, I get the 1. If I factor out a P times 1 plus X from this term, I'm just left with the X. So if I distribute this, if I distribute P times 1 plus X here,
Right.
I get P times 1 plus X times P times 1 plus X times X.
Times that.
The X is here.
It's like the word.
Just if I think of this as, if I think of P times 1 plus X as A. So in this expression I have A plus A times X here. If I factor out an a, I get a times 1 plus x. Does that make sense? So here my a is just p times 1 plus x. I just have a more complicated thing for a.
So the x doesn't just disappear. It's in there somehow.
The x is right here.
Okay.
That's this x. The 1 comes from factoring out this whole term. If I divide this thing by p times 1 plus x, I get the 1. If I divide this whole thing by p times 1 plus x, I'm left with x. Okay? Does that make sense?
Mm-hmm.
Okay, good. All right. This next time, when I compound after the third compounding, now I'm going to do the same thing I did before. I'm going to factor out p times 1 plus x squared. So I get p times 1 plus x squared times 1 plus x. Just like I got before. This time I'm taking out p times 1 plus x squared. And that equals p times 1 plus x cubed. So each time I earn more interest, I can see that I'm adding an exponent on the end here. So finally, after n compoundings, if I compound it over and over and over, my amount is p times 1 plus x to the n. That's how many times I've compounded my interest. So we're going to use this to write our compound interest formula. This is where it comes from. We're going to write it in a way that we're going to use it. Are we good with this? We don't have to memorize this. I just wanted to show you how we get to this formula. All right, so our compound interest formula. Is our amount equals p times 1 plus our interest r over n times nt. A is the amount. P equals a principal, the amount we start with. R is the annual interest rate. N equals the number of pay periods per year. And T equals the number of years. And this formula comes up using the same process that we just talked about, where we keep adding our interest on, and we can keep factoring. We end up increasing our exponent every time we compound our interest. And this is a formula that we've worked with, you guys have worked with before as well. So let's do an example of using the compound interest formula, and then we'll talk about continuously compounded interest. So we have our investment is $5,000. Our interest rate is 6%. This is our annual interest rate. And our time is 10 years. And we want to find the amount that we have. This shouldn't be our A, this should be our principal. Our principal is $5,000. We want to find our amount if our principal is, if we're compounded annually, quarterly, monthly, and daily. So if we're compounding annually, n equals 1, and our amount is 5,000 times 1 plus 0.06 divided by 1 to the 1 times 10. And that gives us, when we calculate that out, 8954.24. N is 1, so our compounding rate is once per year times 10 years. Interest rate as a decimal. And when we do these, remember that you do remember your order of operations, you do the parentheses first, then the exponent, and then multiplication. If n equals 4, this is quarterly. So our interest is compounded quarterly. My amount is going to be 5,000 times 1 plus 0.06 divided by 4 times 4 times 10. And that, if we calculate that out, you should get 9070.98. And we could keep going on with if we wanted to compound monthly. N would be 12, daily, n equals 365. And if we plug these in, we would come up with our amount after, if we compound monthly, is 9096.98. And if we compound daily, we get 9110.14. Just going through the same computation. So we see that as we compound more frequently, our money grows more quickly, but it slows down. Going from daily to quarterly, it makes a good jump, but from quarterly to monthly, it doesn't make that big of a jump, and from monthly to daily, it just makes a little jump. So we're increasing, but we're not increasing faster and faster and faster. It kind of levels out. Now, if we take our compounding period, if we go from daily to hourly to minutely to every second to continuously, so we're continuously compounding our interest. If we do that, then our formula turns into an exponential function with e as our base. So if we compound continuously, our interest continuously, our interest formula turns into our amount equals P e to the R t, where e is the number that we talked about before, the 2.718 number. And if we did our example that we just talked about, where our principal was $5,000, our rate was 6%, and our time was 10 years, if we plug that into this formula, our amount is going to be 5,000 times e to the 0.06 times 10. We would get $9,110.59. And this is our interest compounded continuously. There's no pause in between our compounding periods. We get this exponential function. And let me go back here real quick. You can see how this expression, this 1 plus 0.06 over 1 to the 10th power, that looks like this formula that we used to calculate E. That's why when we compound continuously, as our compounding period gets smaller and smaller, our base turns into our special number E, because this formula and the one we're using here are essentially the same thing. So this is question?
When you're solving that equation, when you just solve the
Uh-huh.
x equals 1000 to the 0.6 times 10, like,
Right.
what do you just plug in a number for E? Or do you
Here,
just
let's pull up the calculator. That's a good question. So on the calculator,
I mean, I know there's like an E button.
Right.
But like, let's say you didn't have a calculator.
if you didn't have a calculator, you'd have to look it up in a table. Back when I was in school, that's what we had to do.
But so you'll give us a calculator.
Yeah, you would use a calculator, and any scientific calculator is going to have an E button. So on this one, let's see it from over here. It is your above your the button that says LN is your second. It says E to the X. So if we wanted to do E. This is E to the whatever power. So if we wanted to do E to the 0.06 times 10, that's how we would do it. And your calculator will tell you that number. And we're going to times that by 5,000. And that's where we came up with, I did 50,000 there, but that's where we came up with our number. And remember, when your exponent, to do an exponent on your calculator, you use this little up arrow button. So to the 0.5, you use this little up arrow button for your exponent. Any other questions on the calculator or calculating exponential functions on your calculator? All right, homework. So we're on page 206.
What if I put this in 0?
And I think you'll find this homework very easy today.